In this lecture, we're going to start a new topic, and that is the power that's radiated by a point charge. And this is actually going to take probably a couple videos to go through because some of the derivation is kind of extensive. So just kind of link these together as you go through the various videos. So the idea is that we're going to kind of start with a charge, Q, which is then going to be moving through space. And as it moves through space, then it will radiate. It'll radiate electromagnetic waves. So the starting point is the electric field that we determined in Chapter 10 for a moving point charge. So that electric field equation was Q over 4 pi epsilon naught, the distance r, over r dotted into the velocity, cubed, times c squared minus v squared, the velocity of the charge, times u, plus r crossed into u crossed into the acceleration. So if you remember, there was an acceleration term and there was a velocity term in this equation for the electric field. So just to remember what the variable was, the variable u was the speed of light in the direction of motion minus the velocity of the charge v. Okay, now for the magnetic field, we determined that it's just 1 over the speed of light times the propagation vector crossed into the electric field. And we can write the pointing vector as 1 over mu 0, the electric field crossed into the magnetic field, which in this case would be 1 over mu 0, the electric field crossed into the propagation vector crossed into the electric field again. So if you were to work out that triple product with the, if you work out the triple cross product, what you would get is 1 over mu 0 times the speed of light, the electric field squared, so E dot E, times R hat, minus R hat dot E times the electric field. Okay. Now, we're only concerned in this particular case in the energy that is in the radiation and not actually the energy in the fields, if that kind of makes sense. So let me explain it a little further. So the idea is that we have this charge which is moving along some trajectory right here. So that's Q. And so what we want to do is to create a surface area around the initial position of the charge and then look at the radiation that's going to be coming out along this vector r, which starts from the charge to the point at which we're measuring the radiation. So here's where we're going to be measuring the electric and magnetic fields along this surface area right here. So we're going to start with the time where the radiation was emitted. So if you look at the change in time, the time now minus the time where the radiation was emitted, or its initial time, and that's equal to the distance that the radiation traveled divided by the speed of light. Okay. Now, since I'm drawing this surface area as a sphere, that means that the surface area goes as 1 over r squared. So we imagine that as the surface area gets bigger, then we spread out the power over top of that surface area. So anyway, higher order terms in R are not going to be related to the radiation. So then I'm just going to simplify things and say that the electric field associated with the radiation is Q over 4 pi epsilon naught R over R dot U cubed times R crossed into the velocity U crossed into the acceleration. So essentially, you're going to get radiation when you have an acceleration. If the particle is accelerating. If it's not accelerating, it's not going to radiate. And then the energy is just in the field associated with that particular charge. Now, the electromagnetic waves in vacuum are transverse, which means that E is going to be perpendicular to R. So R dot E is going to be equal to 0. So the dot product of the propagation vector of the electromagnetic wave is 0. So that means that the Poynting vector that is related to the radiation is going to be just the E squared term. Just that. So the energy of the radiation is associated with the electric field squared. Now we're going to make an assumption, or kind of a simplification, and that is that let's say that the charge is initially at rest. So that means I can write this velocity u as just the speed of light in the direction of propagation. So essentially, the charge is not moving, so I don't have to modify in any way this idea of a frame of reference. So the idea is that me as the observer is not moving with respect to the charge, and the charge is not moving with respect to me initially. At the time that the radiation was emitted, we're going to say that from our point of view, it was at rest. But that doesn't mean that it's not accelerating, because we know that the charge is actually eventually going to gain a velocity. So the initial velocity is 0, but eventually the acceleration of the charge is going to cause it to move and cause it to gain some velocity. So that means that the electric field associated with the radiation is Q over 4 pi epsilon naught C squared R, R crossed into R crossed into the acceleration, which I can now rewrite as R dot A times R hat minus the acceleration. Okay, because what you get is R hat dot R hat gives you 1. Okay, so that's how you get the second term, where it's just the acceleration. Okay, so now I'm going to try and clean things up a little bit and say that epsilon naught times c squared is 1 over mu naught. So I can now write this as mu 0 times the charge 4 pi r hat dot a in the r hat direction minus a, like so. So that means my Poynting vector radiation is 1 over mu naught c mu 0 q over 4 pi r, all the rest of this stuff, So that is squared in the r hat direction. Okay, so now if I square what's inside of those curly brackets, what I should get is mu 0. So I get a mu 0 squared, which cancels one of the mu zeros. Q squared over 16 pi squared C r squared times r hat dot A, quantity squared, r dot r, which is just going to be 1, plus a dot A, which is going to be a squared, minus 2 r hat dot A times r hat dot A, all of that in the r direction. Okay. So what does that give us? That gives us a Poynting vector, which is mu 0 q squared over 16 pi squared C r squared a squared. Basically, you have an r dot a squared and an r dot a squared. So that gives you minus r dot a, quantity squared, in the r direction. Okay. So let's now let theta be the angle between r and a. So that helps us with the dot product. So that means that r dot a is just a cosine theta, and a squared minus a squared cosine squared theta is just a squared sine squared theta, which means I now get mu 0 q squared a squared over 16 pi squared c, the sine theta over r, quantity squared, in the r direction. And so what we have is this kind of donut-shaped radiation again that we had in a previous lecture. Not only that, but if you now take the power as the integral of the Poynting vector over the enclosed area around that donut shape, what you would get is mu 0 q squared a squared over 16 pi squared c, the integral over theta and the integral over phi, and then you would get sine theta squared r squared, and then r squared sine theta d theta d phi, which, now the r squareds cancel. You have to integrate over 2 pi over phi and integrate over sine cubed. And in the end, what you would get is mu 0 q squared a squared 6 pi c, which is the Larmor formula that we derived before. Okay, so we got it by either the general form of an arbitrary source, or you can get it from a point charge, which is now moving.